Okay, so in the last section, we were looking at how to select the model order in a polynomial fitting problem. And we saw that were two different effects. Either you selected the model order that was too low and you got underfitting, and if you selected the model order too high, you got what looked like overfitting. In this section, I want to step back from that particular problem and try to provide a general mathematical framework to understand that in a slightly more rigorous way. And what we're going to do is introduce two very important concepts in machine learning called bias and variance. Both bias and variance are tied to a more general principle called generalization. So to think of what generalization is, let's think about what you do in general in machine learning. You have in general some data points. So if they were just scalar data points, xi, yi, they could just be drawn like these 5 points here. And what we do in essence is from these 5 points, we try to learn the relationship between x and y. In other words, for each x, you're making a prediction y hat with a function f that you've learned from this data. So maybe in this case, you could write that function that you learned like this. Now, implicitly, what you're doing whenever you learned a function is the following. You're saying that now if I give you a new data point, say here x, this function will make a prediction y hat new at that value x. In other words, you're inferring the value inferring the value y at points x that you have not seen in the training data. This idea of inference is also called generalization. The fundamental question in machine learning then is how well do these models that we train generalize to new data points? Or in other words, what can I say about the accuracy of this new data point that we haven't seen? To model or understand generalization, let's go to the following simple model. So imagine I have, again, just variables x and y, and there's some underlying true relationship between these variables captured by this mathematical formula. The formula says that for every x, the y is some function of x, f naught, plus some noise. Of course, you do not know the true function, and the noise is there because there may be other variations in other variations in y not captured by x. And just to make this simple, I've assumed it's Gaussian, but it's not really that important. Now I give you some data points because, of course, the person who's trying to learn this relationship doesn't have access to this. So these are these values in blue. Note that the values of blue are not exactly on this red curve because of this noise term here. And somehow I have to learn this relationship between x and y from these blue data points. So to do this, let's say you have a model. And the model says, okay, for every x, I'm going to make a prediction, f of x, and call that y hat. And this function will depend on some parameters. For example, if it was a polynomial, this would be the coefficients of the parameters. And then, from the training data, I somehow fit beta hat from that data. And that results in some estimated function, which I've shown here in the blue. Now the question then is, how good is this estimate? Or how well did this estimate generalize relative to the true function that's shown here? Well, to do this, I'm going to introduce something called the output mean squared error. And it's just this. Remember that the key idea in generalization is to understand how the function behaves on new data points that have not been in the training data set. So let's imagine that I take a new value of x. Let's call it x test, the test point in this. And this here is some value that I didn't measure the function or didn't measure y at. And I do two things. First, there would be the actual value that you would get at this point. This would be whatever the red value is plus noise. So I've shown that here on this yellow square like this. On the other hand, your inference or your estimate based on your model will predict it on the blue curve that you drew. That I've shown here as y hat. The mean output mean squared error is just simply the expected squared distance between the true and estimated values as shown by this equation. Now, there's a couple important things, just mathematical details. First of all, this expectation is mathematically saying there's randomness in these outputs. And there's two sources of randomness, because there was randomness in the noise in the training data when they tried to get beta hat. And there's also noise in the test data point here. The second part is that when you evaluate this, this will depend on this test value. So this model might have a higher output mean squared error at certain values of x than other values of x. All right, and we're going to try to quantify all of this as we go ahead. Okay, a key property about the output MSE is that you can write it as a sum of two terms. The first term is what we'll call the function MSE. And the function MSE is just the difference between the underlying true function and the estimated function, or at least it's the expected squared difference between these. I'll come back and address this part later. The second term is this what's called the irreducible error. Now recall in our model that the true function is this y, is this true function plus some noise, and sigma squared epsilon is just the variance of that noise. Now this noise occurs because there's some variation in y that is just not related to x. And that, of course, puts a fundamental limit on the ability to predict y. In particular, even if some genie told you what the true function was, you would still have some, if you only knew x, you would still have some variation in y that you simply cannot predict. Just as an example, suppose we went back to the glucose example in the previous unit. Even if I tell you all the attributes of a patient, their age, blood pressure, what they've eaten, and so on, there'll be some, I won't be able to exactly predict their glucose level because there's many other metabolic factors that influence that variable. Now, for our case, this also means that there's a lower bound, if you like, on the output MSE that will always be greater than or equal to this term. So there's a limit to how well we could ever estimate this function. Now, let me just quickly prove this. Just do a little bit of math. It's not that hard. This is what we want to show is that the output MSE is a sum of these two terms. So all we do is pretty easy. Say, well, the output MSE is just a squared difference between y and y hat. And for y, I substitute in our formula. And for y hat, I substitute in this formula. And then I expand the squares and break it into three terms. The first term is just the difference between this minus this squared, but that is just by definition the function MSE. The second term is this squared, but that is just the irreducible error, this term. And the final term is just the cross product between this epsilon and the difference between these two. But we'll just use some independence here to get this. So this is the cross product, this is multiplication between epsilon and these two. But epsilon, the error on the test, we're going to assume is independent of the error in the training data, so we can just use independence to break this expectation out. And then since we know that the error is on average 0, this product goes to 0. So when you put M3 equal to 0, you get the right formula. So this is a very standard little mathematical trick that you use in this case. Okay, to go on, I still want to talk a little bit about this irreducible error term. To do this, let's take a look at something. I want to define a term called the model class. And the model class is just simply the set, if you like, of all possible functions parameterized by this beta. So this is not a particular function, it's a set of functions, like, say, the set of all polynomials of a certain degree. And we'll say that the true function in our model is in the model class if somehow I could theoretically choose at least one parameter called beta naught, where the estimated function exactly aligns with the true function. You may not be able to estimate that parameter, but let's just hypothetically say if it exists. And in this case, we'll call beta naught the true parameter. And we'll say this under modeling whenever the true function is not in the model class. And I'll try to explain why that is relevant in a moment. So let's look at what, before we do this though, let's first make sure we understand the concept of under modeling or not. So just as some little simple questions, I'm going to give you a pair of functions and their model class. You have to see if the true function is in the model class. So let's do a really simple one. Suppose the function is linear, 2 plus 3x, and the model class is, say, second order polynomials. So the question is this true function in this model class? You want to pause the video here if you want to think about it. Okay, now that you've unpaused it, I hope you came up with the answer that there's no under modeling, because obviously if you take the beta to be 2, 3, and 0, you get this function. Obviously, the set quadratic functions include this linear function. If you take the opposite, let's do this, say the true function is quadratic, but the model class is only linear, is there under modeling or not? I'm going to let you pause your video if you need to think about it. Okay, now that you've unpaused your video, I hope that you saw that there was, in this case, there is under modeling. Whatever I pick for beta 0 and beta 1, I'm not going to be able to capture that x squared term here. Let's do 2 more examples. All right, let's say that the true function is this sinusoid, and the model class includes the sine and cos, but in this case, there's no phase here. This one's a little trickier. Do a little bit of algebra, and I'll let you pause again. Okay, now that you've unpaused, maybe you came up with this solution. In this case, there's no under modeling, but to do this, you have to do a little bit of trigonometry. If you remember the form for sine A plus B back from high school, you can do that, apply that here. The true function you can rewrite as sine x plus sine A cos B plus cos A sine B, and you get this. And then when you do this, you can line these up, select beta 0 to be cos of 7, beta 1 to be sine of 7, and now this function is written in this form. So sometimes it's not always obvious that the true function is in the model class. Okay, let's do a closely related one. There's the true function. It's almost the same, but note that the frequency of this sinusoid is 8, and it's 5 here. Let you pause the video again. All right, now that you've unpaused it, hopefully you saw that there was no under modeling, because there's no way either a sine or a cosine term with a frequency of 8 can ever be matched with a sine or cosine with a frequency of 5. Okay, now that you understand what we mean by the term model class and true function, let me show you its importance in this context. So let's say that there is no modeling. So somehow I've picked my model class, no undermodeling. So somehow I've picked my model class so large that there's some true parameter in which that matches the true function. And somehow, a big if, the estimator is able to find this parameter. Let's just say that both of these two things are true. Find this true parameter. Well, in this case, there are two important implications. First, if you look at the function MSE, it will just be f naught minus f. But this here is because in this case, the true function matches the estimated function. The function MSE is 0. So that term, the output MSE, is gone. And when that term of the output MSE is gone, we're left with the irreducible error, just sigma squared, epsilon. Now, what's the implication of this? So if there's no undermodeling, so the true function is in the model class, and somehow we can estimate the true parameter, we'll see if that's really possible or not, then we can say that the output MSE is just the irreducible error. In other words, we can achieve the same error as if we knew what the true function was. So that's great. That's the best we could ever do. And this tells you, well, how do I get to this? At least for the first part, to get to there's no undermodeling, I should just pick my model class to be really, really large to make sure that the true function is in that model class or very close to that model class. So if you were doing, say, the polynomial fitting, what I would do is pick the polynomials with very, very high degree, like a 14th order or something like that, to make sure that whatever the underlying relationship is, it will capture it. But we're going to see in the next section that there are problems when we use very large model orders. But before you do this, I want you to try the in-class exercise, which is just basically the same type of problem that you saw. Make sure you understand what a true function is and a model class. The solution and the problem are on the GitHub site, and once you do that, go ahead to the next section.